When we talked about atomic structure, we said that a heavy nucleus that consists of protons and neutrons is located in the center of the atom. The nucleus is about 100,000 times smaller than the atom itself, but contains most of the atom's mass. We also said that somewhere around the nucleus we can find electrons, and that in a neutral atom the number of electrons that have a negative charge must be the same as the number of protons that have a positive charge of equal magnitude. Now the time has come to think about how electrons are arranged around the nucleus. The arrangement of electrons is important because it determines how atoms can connect with other atoms to form everything around us. Unfortunately, in this class we can't discuss the reasons behind the particular arrangement of electrons in atoms. These reasons are explained in detail by a branch of modern physics called quantum mechanics. However, we will learn how to determine the arrangement of electrons in any atom of a given chemical element, referred to as the atom's electron configuration. The first thing we need to note is that it is impossible to know where exactly electrons in an atom are located at any given moment in time, and how exactly they move. A fundamental law of nature that was discovered by the German physicist Werner Heisenberg and is known as the uncertainty principle is responsible for the state of affairs. We can only know how likely it is to find an electron at various points around the nucleus. The regions of space around the atomic nucleus where electrons are likely to be found are called orbitals. An orbital is not the same as an orbit. An orbit is the path that, say, a planet that moves around the sun follows. We can't know the specific path that an electron follows around the atomic nucleus. So an orbital is like a map that shows the probability, that is the likelihood of the electron being at each point inside the atom. The second thing we need to note is that another fundamental law of nature, discovered by the Austrian physicist Wolfgang Pauli and known as the exclusion principle, prohibits more than two electrons from being in any given orbital. Therefore, if an atom has more than two electrons, as the atoms of all elements except hydrogen and helium do, the electrons have to be distributed between more than one orbital. We will talk about how exactly electrons are distributed between different orbitals in the next lecture. For now, let's have a look at the orbitals themselves. Orbitals come in different shapes and sizes. Based on their shape, all orbitals can be classified into four types. S orbitals are spherical. P orbitals are dumbbell-shaped. D orbitals are shaped either like a flower with four petals or like a dumbbell with a bagel around the middle. And F orbitals have even more complex shapes. A group of orbitals of the same type, S, P, D, or F, and of the same size is called a subshell. An S subshell only contains a single S orbital. A P subshell contains three P orbitals that are oriented perpendicularly to one another. A D subshell contains 5 D orbitals, and an F subshell contains 7 F orbitals. Orbitals differ not only in shape, but also in size. For instance, spherical s orbitals can be smaller or larger. The s subshell that consists of the single smallest s orbital is referred to as 1s. The s subshell that consists of the single second smallest s orbital is referred to as 2s. The s subshell that consists of the single third smallest s orbital is referred to as 3s, and so on. As we already said, a p subshell consists of 3 orbitals. These 3 orbitals are of the same size, but the direction along which the dumbbell is oriented is different for them. The subshell that consists of the three smallest p orbitals is referred to as 2p. The subshell that consists of the three second smallest p orbitals is referred to as 3p. The subshell that consists of the three third smallest p orbitals is referred to as 4p, and so on. Notice that there is no 1p subshell. A d subshell consists of 5 orbitals. The subshell that consists of the 5 smallest d orbitals is referred to as 3d. The subshell that consists of the 5 second smallest d orbitals is referred to as 4d. The subshell that consists of the 5 third smallest d orbitals is referred to as 5d, and so on. There are no 1d or 2d subshells. Finally, an f subshell consists of 7 orbitals. The subshell that consists of the 7 smallest f orbitals is referred to as 4f. The subshell that consists of the 7 second smallest f orbitals is referred to as 5f, and so on. There are no 1f, 2f, or 3f subshells. The number before the letter that indicates the subshell type, S, P, D, or F, is known as the principal quantum number. All orbitals that have the same principal quantum number make up a shell. So the first shell only consists of one subshell, 1s, which consists of a single spherical s orbital. The second shell consists of two subshells, 2s that consists of a single spherical s orbital, and 2p that consists of 3 dumbbell-shaped p orbitals. The third shell consists of 3 subshells, 3s that consists of a single s orbital, 3p that consists of 3p orbitals, and 3d that consists of 5d orbitals. The fourth shell consists of 4 subshells, 4s that consists of 1 s orbital, 4p that consists of 3p orbitals, 4d that consists of 5d orbitals, and 4f that consists of 7 f orbitals. All subsequent shells are similar to the fourth. The fifth shell consists of 5s, 5p, 5d, and 5f subshells, and so on. If you have ever taken physics, you might remember that energy is a physical quantity that describes how much work an object can do. For example, a compressed spring in a catapult has enough energy to launch Wile E. Coyote high into the air, and the gasoline that you put in your car has enough energy to propel it. We won't talk much about energy in this class, although it is important in chemistry. But I should tell you that electrons in different orbitals within the same subshell of the same shell have the same energy, and electrons in different subshells and/or in different shells have different energy. If we consider the same subshells of different shells, say the 1s, 2s, 3s, 4s, and so on subshells, we will find that the electrons in subshells of shells with larger principal quantum numbers have more energy. If we consider different subshells within the same shell, say 4s, 4p, 4d, and 4f, we will find that electrons in the s subshell have the least energy. Electrons in the p subshell have more energy. Electrons in the d subshell have still more energy, and that electrons in the f subshell have the most energy. But what about the energies of electrons in different subshells of different shells? For instance, the electrons in 4s have more energy than electrons in 3s, and electrons in 3d also have more energy than electrons in 3s. So do electrons in 4s or in 3d have more energy? You can find out in the following way. Write out the subshells so that all subshells of the same shell are in the same row, and the same subshells of different shells are in the same column, as on the slide. Then draw diagonal arrows as shown, and write out the subshells in the following order. First, moving along each arrow from top right to bottom left. Then, once you have finished all subshells along an arrow, moving to the arrow right below it. So you will get 1s, and moving on to the second arrow from top, 2s, and moving on to the third arrow from top, 2p, 3s, and moving on to the fourth arrow from top, 3p, 4s, and moving on to the fifth arrow from top, 3d, 4p, 5s, and moving on to the sixth arrow from top, 4d, 5p, 6s, and moving on to the seventh arrow from top, 4f, 5d, 6p, 7s, and so on. The sequence of subshells is in the order of increasing energy of electrons that are found in, or as we say in chemistry, occupy these subshells.